So if you think about it, for the last decade or so, we've basically been carrying around these incredibly powerful terminals in our pockets.
Oh, absolutely. I mean, we call them smartphones, but
Yeah, but really they're just like glass doors to the cloud.
that's a good way to put it, actually.
Because when it comes to any real heavy cognitive lifting, you type a prompt and it shoots up to some massive centralized server farm, humming out in the desert somewhere.
Right, and then the answer just gets beamed back to you. It's the fundamental architecture of the modern web, really.
Exactly. We've all just kind of accepted that if you want true frontier-level artificial intelligence, you have to rely on heavy, centralized infrastructure.
Yeah, you have to rent time on someone else's supercomputer, and the latency, the privacy issues, the bandwidth.
Which is the tax you pay, right?
Exactly. It was considered the necessary tax for that high-level compute.
But looking at the document provided for Google DeepMind's new Gemma 4 family, which, just dropped 2 days ago on April 2nd, 2026, it seems like they're trying to completely sever that tether to the cloud.
They are, and that's exactly what we're going to unpack today.
Right, so welcome to this deep dive. Our mission today is to go through the technical documents, the official model cards, and the benchmark data they supplied, because this isn't just some incremental update where your chatbot gets a little better at writing emails.
No, not even close. What we're looking at in the provided document is a generational leap in open weight models.
And these are designed specifically to run natively on your local devices, right? Which is wild for you listening, because imagine an AI that understands images, processes audio, and does multi-step reasoning, all without a single bar of Wi-Fi.
The shift in power dynamics here, honestly, it cannot be overstated.
Yeah.
Yeah, because by packing all these native multimodal capabilities into open models, DeepMind is effectively taking the power of a cloud monopoly and just, well, handing it directly to developers.
And everyday users, too. But to really grasp why this is so disruptive, we have to look at the core design philosophy in the supply document. There's this recurring emphasis on agentic workflows.
Right, and that's the key term here.
I want to stop right there, actually, because agentic is one of those buzzwords that gets thrown around constantly.
Oh, definitely. It's everywhere right now.
Up to this point, for most of you, your interaction with AI has been transactional. Like, you ask a question, it predicts the next string of text, and you get an answer. It's basically a really smart encyclopedia.
Exactly, a passive responder.
But the document provided insists this model transitions from a passive responder to an active planner. So mechanically, what does that actually mean under the hood?
Well, the mechanical difference really comes down to how the model handles output generation and external tool calling.
Okay, break that down for me.
So a traditional language model is trained mostly on conversational prose, right? It wants to give you a natural language answer.
Right, it wants to chat.
Exactly. But Gemma 4 is heavily optimized for structured reasoning, specifically native JSON output.
Okay, wait, JSON is just a standardized data formatting language, right?
Yeah, pretty much.
So why does spitting out a specific data format magically turn a chatbot into an agent?
Because the entire digital world, every API or application programming interface communicates through structured data, not English.
Oh, right. Servers don't read conversational English.
Exactly. If you want an AI to actually, book a flight for you, update your calendar, or search a database, it has to trigger external code.
And that code needs precise inputs.
Right. It requires predictable, perfectly formatted data structures. And in the technical document they supplied, it shows Gemma 4 is trained to natively output those strict formats.
So it can talk to your device's operating system directly.
Yes. It interfaces directly with web APIs. It doesn't just give you instructions on how to do something. It actually generates the exact code payload required to execute the action, reads the response back, and then plans the next step.
Okay, let me see if I have this right. It's like, instead of just handing you a recipe for dinner, an agentic workflow is like hiring a personal assistant.
That's a great analogy, actually.
Like, it checks the inventory API of your smart fridge, figures out what you're missing, generates a JSON payload to add those missing ingredients to your grocery app, and then confirms the delivery.
Precisely. It's bridging the gap between just thinking and actually doing.
That's incredible.
And DeepMind achieved this by optimizing a metric they call intelligence per parameter.
Right, parameters being the synaptic weights of the network.
Yeah. Usually, if you want more intelligence and reliable tool calling, you just need a massive parameter count.
Which means you need massive VRAM, video RAM.
Exactly. But what's fascinating here is that DeepMind engineered these models to punch wildly above their weight class. They're matching proprietary models that are, up to 20 times larger.
Okay, so let's dig into the hardware requirements then. Because if this model is doing all this multi-step API routing and holding long context, the math on running this locally just starts to sound physically impossible.
It does seem counterintuitive, yeah.
Based on the provided document, DeepMind split the Gemma 4 family into two main tiers, right? The edge models and the workstation models.
Correct.
So looking at the edge models first, the E series, we have the E2B sitting at about 2.3 billion effective parameters and the E4B at 4.5 billion.
Right, and both of those are optimized for low latency.
Yeah, the documentation even mentions running these on a Pixel phone or like a Raspberry Pi. But here's the spec that absolutely broke my brain.
Let me guess, the context window.
Yes. Both of these tiny edge models boast a 128,000 token context window.
It is a staggering spec for mobile hardware, honestly. Processing 128K tokens is roughly equivalent to holding a 300-page book in active memory all at once.
How is that even possible? I mean, how does a phone physically hold 128,000 tokens in active memory without just melting the processor? Because standard transformer architecture has that memory bottleneck, right? Where every single word has to mathematically attend to every previous word.
Right, the n-squared bottleneck. You've identified the exact reason large context has historically been kept out of edge devices. The VRAM required just scales exponentially.
So how do they bypass it here?
According to the document provided, the mechanism they use is an optimized form of sliding window attention.
Sliding window attention. Okay, what does that mean in practice?
So instead of forcing the model to calculate the relationship between the current token and all 100,000 previous tokens simultaneously.
Which would fry a phone.
Right. Instead, the attention mechanism uses a fixed size window that slides over the text.
Oh, I see. So it's caching the relationships in smaller kind of overlapping chunks rather than trying to process one massive matrix?
That is the core of it, yeah. It maintains a highly compressed key-value cache, or KV cache, of the older tokens.
Makes sense.
So it only brings the most immediately relevant tokens into the heavy computational window. It drastically slashes the memory bandwidth you need.
Wow. And, another thing I noticed in the supplied document, they list the E2B as having 2.3 billion effective parameters, but 5.1 billion if you count the embeddings.
Right, which highlights a very deliberate architectural choice by DeepMind.
Let's clarify embeddings really quick for anyone listening who might run these models but hasn't really dug into the architecture. We're essentially talking about the vocabulary lookup table, right?
Yes, exactly. The embedding layer is the dictionary. It translates human text, or in Gemma 4's case, image and audio data, into the mathematical vectors the neural network actually computes.
Right, the language of math.
And DeepMind massively expanded that embedding layer so it could natively handle this multimodal input without needing external translation models.
Oh, so the brain doing the logic is only 2.3 billion parameters.
Yeah.
Because it makes it super fast. But it has this massive 2.8 billion parameter sensory system feeding it data.
That's a perfect way to visualize it. Fast logic, huge sensory input.
Okay, so that's the edge tier. Stepping up from that, we get into the workstation tier, which is designed for laptops and local servers.
Right, where you have a bit more thermal headroom.
Yeah. So we have a 31 billion dense model, which has a massive 256,000 token context window. But the architecture that really stands out in the technical document is the 26B A4B.
The mixture of experts model.
Exactly. It uses a MOE architecture. And I've always thought of mixture of experts as being like a giant corporate team.
Okay, let's hear the analogy.
So you have this massive payroll with all these employees, but when a math problem comes in, you only wake up the accountant. You don't make the marketing teams sit there and do calculus, so you save a ton of energy.
I like that. That captures the high-level concept perfectly.
But mechanically, how does that actually work?
To be mechanically accurate, we have to look at the router network.
The router.
Yeah. So in a dense model like the 31B, every single parameter processes every single token of your prompt. It's highly capable, but computationally very expensive.
Right. Everyone in the company is working on the same problem.
Exactly. But in the 26B MOE model, there is a gating network, which is the router. It evaluates every incoming token and dynamically assigns it to only the top 2 expert subnetworks that specialize in that specific type of data.
Oh, wow. So while the total file size on your hard drive contains 26 billion parameters, the actual compute cost during inference is way lower.
Drastically lower. The VRAM bandwidth being utilized at any given millisecond is tiny by comparison. It only activates about 3.8 to 4 billion parameters per forward pass.
That is incredibly efficient.
It is. And when you combine this MOE routing with advanced quantization,
Which is basically compressing the model weights, right? Like reducing the mathematical precision from a 16-bit float down to a 4-bit integer.
exactly. When you do that, the memory bandwidth required to fetch those weights from your VRAM to the compute cores is slashed. This is why you can get blazingly fast tokens per second generation on consumer laptops.
Without needing some industrial GPU setup.
Right.
But, routing efficiency and data compression don't automatically equal rigorous logical accuracy.
That's a very fair point.
Because sparse MOE models sometimes really struggle to maintain a coherent chain of thought compared to massive, dense models, since the data keeps jumping between different expert layers.
Yes, that has been a historical issue with MOEs.
So how does Gemma 4 actually hold up when we look at the benchmark data in the provided document? I mean, we need to see if this native thinking actually translates to real results.
Well, the verified data from this April 2026 release is what really elevated this from an interesting architectural paper to a major industry disruption.
Yeah, lay it on me.
If we look past the standard conversational benchmarks and focus entirely on rigorous sequential logic tests.
Like the math stuff.
Exactly. Let's look at AM 2026, which is a very advanced mathematics benchmark. The Gemma 431B dense model scores 89.2%.
Wait, 89.2%.
Yes. And for context, the previous generation, the Gemma 327B model, only hit 20.8%.
That is, jumping from 20% to nearly 90% in advanced math in a single generation is just wild. How did they do that? Did they just aggressively train this on more math textbooks?
No, you can't just brute force a model with more math textbooks to get an 89% on AM. Language models don't really do math in the way a calculator does. They're predicting tokens.
Right.
That massive leap is the direct result of the structured reasoning we discussed earlier. The model has been trained to output thought tokens before it ever commits to an answer.
Thought tokens. So it's basically thinking out loud.
Essentially, yes. It breaks the mathematical problem down into sequential steps, verifies each step against its internal logic, and only then generates the final output.
Ah, I see.
So high performance in advanced math is basically a proxy for a model's ability to hold a long chain of thought without hallucinating.
And if it can hold a rigorous chain of thought in calculus, it stands to reason it can hold a rigorous chain of thought when, say, managing a file system or executing code.
Precisely. Which brings us to the benchmark that actually proves those agentic claims, the tau-squared bench.
Right, the tau-squared bench. What exactly does that test?
It's a crucial metric that tests agentic tool use in simulated real-world environments. Like, imagine navigating a retail database to resolve a customer service ticket.
Oh, so it's not just answering a question, it's doing a task.
Right. The model has to maintain a state, query in an API, read the database response, realize it needs more information, query a second API, and then actually execute a refund.
So it's testing the exact JSON payload generation and external tool triggering we were talking about earlier.
Yes. And in the supplied document, Gemma 4 scored 86.4% on the tau-squared bench.
Wow.
That level of reliability is the absolute prerequisite for handing an AI the keys to your device. If a model hallucinates its API calls even, say, 30% of the time, it's useless as an autonomous agent.
Yeah, it would just break your computer.
Exactly. Hitting nearly 87% proves the architecture is incredibly sound. And even more impressive, the tiny E4B Edge model.
The one running on a phone.
Yeah, that one hits 52% on LiveCode Bench, which tests competitive coding.
That is just crazy. Having this level of frontier reasoning natively on a device it's incredible.
It really is.
But looking at the broader landscape, the most disruptive part of Gemma 4 isn't just its benchmark scores, right? It's the licensing. DeepMind released this under an Apache 2.0 license.
Which is a massive deal.
Right, and the audience here generally knows the benefit of open weights. But in the context of the current AI race against models like Llama 4 and Qwen, why is an Apache 2.0 license such a huge differentiator?
Because it completely removes the ambiguous legal friction that has plagued a lot of other supposedly open models.
Like what kind of friction?
Well, some community licenses come with acceptable use policies that restrict what competing products you can build. Or they include user-based caps.
Oh, meaning if your startup suddenly gets a massive influx of monthly active users, you suddenly owe licensing fees.
Exactly. Apache 2.0 is one of the most permissive licenses available. It effectively guarantees commercial freedom, modification, and redistribution without those corporate tripwires.
So just to be clear, a developer could take the 26B MOE model, fine-tune it specifically for proprietary medical research, package it into an offline app, and sell it commercially without looking over their shoulder at Google's legal team.
They absolutely could, and that is the promise of true digital sovereignty. Because you have the weights locally, the data never leaves the device.
Right. The privacy implications for sectors like healthcare or law or enterprise coding, they're just profound.
They really are.
It sounds like a massive leap forward. But, we also have to look at the friction points because
Yeah.
open source of this magnitude is kind of a catch-22.
Oh, absolutely. There are always trade-offs.
It brings immense power, but there are practical limitations that the spec sheet might, gloss over.
Okay.
Let's talk about that context window again. 256,000 tokens on the workstation model sounds amazing, but broader academic research into scaled attention shows that performance usually degrades significantly in massive documents, doesn't it?
It does. It's widely known as the needle in the haystack problem,
Yeah.
and it's a fundamental mathematical limitation of current attention mechanisms.
How so?
When you drop a 200-page PDF into a model, the attention mechanism has to distribute its focus, a probability mass across all those thousands of tokens.
Right.
As the denominator in the softmax function grows with the context length, the attention basically gets diluted.
So the model might perfectly recall the introduction and the conclusion, but a critical, isolated fact buried on page 114 just gets completely washed out in the mathematical averaging.
Exactly. Having the window open that wide doesn't automatically guarantee the model is deeply comprehending every single sentence. It often requires careful prompt engineering to force it to retrieve specific data from the middle of a huge context block.
That makes a lot of sense. Furthermore, while the provided document highlights that Gemma 4 supports over 140 languages, we have to apply the same scrutiny here that we apply to all frontier models.
Definitely.
Because the underlying training data across the entire internet is, well, it's overwhelmingly English-centric.
The disparity is vast. When a model is fundamentally trained on English data structures, its logical reasoning is effectively thinking in English.
Even when it's speaking another language.
Yes, when it operates in secondary languages, particularly low-resource languages, we often see subtle degradation in logical coherence or cultural misalignment.
So the translation might be grammatically perfect, but the underlying reasoning pathway is just less robust.
Yeah, it's a critical nuance for developers building global applications.
But I'd say the biggest catch-22 with an Apache 2.0 release of an agentic model has to be the safety aspect, right?
Undoubtedly, that is the elephant in the room.
I mean, Google surely performed rigorous safety alignments on Gemma 4 before release to prevent it from generating malicious code or actionable harm. But open weights fundamentally mean you are handing over the core engine.
This is the most profound challenge of the open source movement right now. With a proprietary cloud model, if a bad actor figures out a jailbreak, the corporation can patch the vulnerability on their servers instantly, cutting off access.
Right, they just update the API.
But with open weights, the genie is completely out of the bottle. Bad actors can intentionally strip away the safety alignments through fine-tuning.
Because if the model is capable of generating structured JSON to autonomously operate a file system and you remove the ethical guardrails, you suddenly have an incredibly capable, locally run malware generator.
Exactly. The capabilities themselves are entirely neutral. It is the application that dictates the outcome.
That's a scary thought.
It is. This release fundamentally shifts the burden of safety from a centralized corporation to the open source collective. The community doesn't just benefit from free access to frontier models anymore. It now bears the immediate responsibility of developing dynamic, defensive architectures.
So we have to build local systems that can actually monitor and quarantine malicious fine-tunes.
We have to, yeah, because there is no central off switch anymore.
Wow. So bringing this all together for you listening, what we are witnessing with the Gemma 4 launch in this provided document is the definitive proof of concept that local open-weight AI can genuinely rival proprietary cloud monopolies.
Truly.
We aren't just talking about chatbots anymore. We are looking at natively multimodal models that use advanced routing and quantized architectures to fit massive intelligence into consumer hardware.
And they can hold rigorous chains of thought, execute complex agentic workflows, and do it all with complete data privacy.
All under an Apache 2.0 license. It really is a profound democratization of intelligence, despite those inherent challenges in hardware limits and safety.
It is. But, as we transition away from this centralized factory model of AI computing, I want to leave you with a broader implication to consider.
Right. What's the final takeaway?
Well, if we are truly entering an era where our most powerful multimodal AI agents can reason, plan, and execute complex multi-step tasks entirely offline on the devices we carry every day,
Yeah.
how will this redefine our society's absolute dependence on constant internet connectivity?
Whoa.
For the last 2 decades, losing your connection meant losing your capability. But if our primary tools no longer need the cloud to think or parse our environment, the very architecture of how we live, how we work, and how we interact with technology might be about to fundamentally shift back to the edge.
A supercomputer in your pocket that finally does its own thinking without needing a signal. That is something to mull over. Thanks for joining us on this deep dive. We'll see you next time.